All right, what we did in class today we'll call 9.2, and that really focused on 12.2 in the book. This we'll call 9.3, and obviously focuses on 12.3 in the textbook. So today we're going to talk about determining the form of the rate law. And to do that, we're going to use the method of initial rates. I'm going to go through a couple bullet points here. We have a lot of text. If you need to pause and write, do so. I'm going to talk quickly. The value of the initial rate is determined for each experiment at the same value of t as close to t equals 0 as possible. So what is the rate of the reaction at the initiation of the reaction? Several experiments are carried out using different initial concentrations for each of the reactants, and the initial rate is determined for each individual run. The results are then compared and graphed to see how the initial rate depends on the initial concentrations of each of the reactants. So that's the process of the method of initial rates. From that process, we're going to be able to find a rate equation that will look like the general form like this, like we saw in class. And from that equation, we'll be able to develop the overall reaction order. The reaction order is just going to be the sum of the exponents in the reaction rate. So if n were 1 and m was 1, 1 plus 1 is 2, this would be a second order reaction. That number, second order, third order, fourth order, will tell us the rate at which the products are going to be produced. Again, K is the constant, brackets with the letter inside to tell us the concentration of said letter. Let's do an example to highlight the method of initial rates now. Alright, so we've got this equation. We've got ClO2 plus some fluorine gas to make the product on the right side of the yield 0. We can probably, I think we're comfortable writing this as our general rate equation. Rate equals some constant K times the concentration of fluorine raised to the x power, ClO2 raised to the y power. The question is obviously going to be, well, what is x and what is y? Let's take a look at the data that we've been given from the experiment. What happens when we double F2? And we want to keep ClO2 constant, but we want to double F2. Right now, the ones that are circled on here are the characteristics that I'm looking at. So experiment 1 and experiment 3. If we double F2 from 0.1 molar to 0.2 molar, and we keep ClO2 constant, we want to know what happens to the initial rate. Well, it doubles. Here you go. So it goes from 1.2 times 10 to the negative third to 2.4 times 10 to the negative third molar per second. So again, we went ahead and doubled F2, and that had the effect of doubling our initial rate. Well, what does that mean? Well, that means that x equals 1. If the process by which you are increasing the concentration, if that change equates this change in reaction rate, so if it's the same on here as it is here, we doubled here and we doubled here, that means that you have a first order reactant. All right, now let's check out the ClO2. All right, we quadruple ClO2 and we keep fluorine constant. So fluorine stays at 0.1. ClO2 goes from 0.01 to 0.04. So we quadruple it, 4 times as much for this particular experiment. And what happens? The rate quadruples. Check it out. It goes from 1.2 times 10 to the negative third to 4.8 times 10 to the negative third. So we quadruple the reactant, and the rate quadruples. So what do you think the rate exponent is going to be? 1 again, exactly. So now we know what our exponents are. So we can rearrange our equation. We can substitute 1's in for those superscripts, and we know that we generally never write to the 1's power. So this would be our finished rate equation. Okay. Let's do some other examples now. We want to know what is the order of this particular vague reaction with respect to A. Okay, what's the order with respect to A? Let's take a look. Well, when do we hold B constant? That's between experiment 2 and 3, right here and here, right? At that point, we double A. Okay? So we take A from point 1 to point 2, or from 1 to 2. What happens over here with our initial rate? It was 2.5. It's still 2.5. So that means a doubling of A has really no net effect of changing the rate of the reaction. Well, what does that mean our order is with respect to A? It's 0. Interesting. All right, let's check B now. What is the order with respect to B? So we got to hold A constant. Hold A constant. We only want to change one variable. With B, then, we're going to go from 1 molar to 2. What's the effect on our rate? Well, it was 1.25 times 10 to the negative second, and it doubles right there. So our rate with respect to B is 1. So the overall reaction order is 1. And think about the reaction rate for this particular equation now. Rate equals K, A to the 0 power, B to the first power. Well, what can we do with the A? What is anything to the 0 power? 1, right? Yeah. So, well, bye-bye, A. The only thing that this particular reaction depends on is the concentration of the B. And we don't have to write the exponent. Go. So that would be our rate equation for this particular chemical reaction. Let's try another one. What is the order with respect to chlorine in this particular example? So now let's use an actual substance. Again, we got to look at the other reactant and see when we hold it constant. That's right there and right there, 0.25 and 0.25. Well, in those cases, what do we do to chlorine? We go from 0.25 to 0.5. Well, what happens to our initial rate? Check it out. It doubles. So when we double chlorine, we double our rate. All right, so that's 1. Now let's check out what happens with the nitrogen monoxide. If we hold our chlorine constant, there and there, we go ahead and double this guy, what happens to our rate? Yeah, that triples, doesn't it? We can go ahead and do the math. All you got to do on your calculator is take this number, okay, and divide it by this number. It's a little confusing sometimes because of the exponents, okay, but don't let that confuse you too much. All right, so that guy divided by that guy, and what do we get? We should get 3, right? Or 2, rather. I'm sorry, 2. You guys are all thinking 3. What the heck? All right, so, you shouldn't get 2. I'm sorry. You should get 4. And here's why. This is why I was confused. All right, so if you go ahead and you double this, okay, you're doubling that one. Come over and you look at the rate. Oh, that's increasing by 4 times. Okay, that's increasing by 4 times. This number, in order to get the 1.14 times 10 to the negative 5th, we got to multiply it by 4. So the rate's increasing by 4 times. So if we double the concentration here, our rate quadruples. That means it's a second order with respect to NO. So if you double it and your rate quadruples, that's a second order. So the overall order, we just add those two up, we have an overall order of the reaction of 3. Okay. So we actually want to determine the rate law for this one. We want to determine the rate law and calculate the rate constant. So we're going to actually calculate the constant, that's K, for the following reaction from the following data. Okay, so we have 3 different experiments. We have a couple of different initial rates here. All right. So here's our vague equation, our general equation. We know both of our reactants, S2O8 and I negative. We want to know what K, X, and Y are. Well, first of all, let's take a look at what happens when we hold S2O8 constant. And when we do that, we are actually halving. Okay, we're cutting the concentration of I in half. And what happens to our rate? It also cuts in half. So as it pertains to I, we have a first order. Okay. Now what happens when we keep I constant? When we keep I constant, we double. Okay, we double S2O8. And what happens to our rate? It doubles. So again, another first order. Okay. So double I negative, the rate doubles from experiment 1 and 2. So y equals 1. If we double S208, the rate doubles from experiment 2 and 3. We've got x equals 1. So we've got 1 and 1 in place of the x and the y. Okay? So this is what we know so far. Now we need to figure out k. Well, k, remember what this equals. K equals the rate divided by the concentration of S208 times the concentration of I negative. Well, here's all we got to do. Let's just pick something we like. Let's say we like this top one, right here. We're going to take all those numbers and we're going to plug them into that equation. You can see that those numbers are the numbers that are plugged into this equation. So if you equal that out, you're going to find a rate constant K of 0.08. There it is. That's your rate constant K. So now we can actually write the actual rate law for this particular process. All you got to do is substitute this guy in for K, and we're all set to go. That's it. We'll talk about integrated rate law tomorrow in class, or maybe tomorrow with notes, one of the two.